Good morning, doctor. Welcome to my presentation. I'm Vincent Lee Jixiang, and I'm here today to talk about static. And my title is Bridge Design and Load Testing. So let's start by looking at abstract. So for our objective today, we're going to design, construct, and test a possible stick bridge to evaluate its structural strength and load bearing capacity. So we select the Warren Strauss design for its ability to evenly distribute force. So we construction of the bridge using a popsicle stick and glue, and secondly, incremental application of weight to observe a deflection and determine a maximum load capacity before its failure. So for the result, the maximum load capacity is 4.5 kg, and how we failure because the joints due to the glue limitations. So we can conclude that the truss design successfully distribute weight and the limitation joint strength and material consistency. So how we improve? We can enhance the joints reinforcement and ensure material uniformity for improved performance. So we can understanding of basic engineering principle, and we can highlight the importance of design and material selection in structural performance. So now let's move on to the introduction. So for the history of bridge, it is the transportation network for thousands of years until now. So it's highlight the importance of structural engineering, material science, physics in load distribution. So what we got the modern challenge nowadays, our bridge design remains essential of aspiring engineers to study. So we can assign that it is success in bridge design depends on the material selection, design ingenuity, and understanding limitation. So we can learn from the past failure and understand the force like tension, compression, and shear. So here are the experiment overview. So for process, we can design the bridge based on the Pacific criteria and construct a model bridge. So the incrementally apply loads to determine the maximum load bearing capacity before failure. So what we can learn about, we can explore the mechanical properties, we can understand the principle like structural integrity, and we can gain the practical experience. So here are the relevance and outcome. So he's the Archimedes of Syracuse. So he's from the ancient city of Syracuse in Sicily. So although few details of his life are known, he is regarded as one of the leading scientists in classical antiquity. He did a pioneer work in static. So he is typic. So he instead proposed a theory of motion in which both the upward and downward motion are caused by weight. So turning to the next point is theory. So we can see the diagram. So when the load is placed, the downward force will act on the bridge model, and the F on the model is given by F equal to mg. At the same time, the tension will be acted also at the connection, the load, and the base on bridge. So the T formula is T equal to mg. So when the load is placed and the bridge model be stable, the equilibrium force achieved. So T with force will be same. So T equal to F and F equal to mg. So we can apply the Newton's second law in static. So F equal to ma. So for static equilibrium, so A equal to 0, therefore F equal to 0. So summation of moments in equilibrium, so m equal to I alpha and equal to 0. So we go to force on hanging object. So for downward force, which is gravity, so F equal to mg, and the g is 9.81 ms power of negative 2. So for the upward force, which is tension, is T equal to mg. So here are the types of forces, which is contact force and body force. So here are the important points we can mention, which is a particle is in equilibrium when the resultant of all forces is 0, and the equilibrium equation in a triangle coordinate system, which is the sum of forces in all three directions equals to 0. And we can determining the tension in cables. So here are the material stiffness and load capacity, the explanation. So this is the problem statement. So how are the different material and structure affected to the maximum weight that the bridge until its failure, which means it will break. So this mentioned before. So to test the bridge, can effort how many the load capacity and the structural integrity. So move on to methodology. So here are the apparatus, and let's move on to the procedure. So for step 1, okay, we construct the bridge and we set up all the things, and we rigging the loads. So we added lah. So like we add one time, we record one time, we add one time, we record one time. So we also collect the result, and finally we plot the data. So let's see what we can observe. So as you can see, our apparatus setup is like that. So we increase the mass of the load, and we measure and record the deflection of popsicle stick. So we can go to result. So for the weight and deflection, and you can see when the weight in kg is added, the deflection will be added. And let's move on to calculation. So for calculation, we can see the graph. Okay, as you can see in the graph, as I mentioned before, when the weight is increased and the deflection also increased. And here are the calculation. We use K equal to W over D. K is the stiffness, and W is weight, and D is corresponding change in deflection. So we use the data we collect in the graph, and we can get the K equal to 6.6 times 10 power of negative 0 and M power of negative 1. So let's move on to discussion. So the discussion a little bit more. So we go through fast. Okay, so as you can see, the static theory explained in the expression result. So according to static equilibrium, the sum of forces and moment must balance to maintain stability. So, and this Warren Truss design can help to distribute weight evenly to the support. So the deflection vs load graph indicate, like we can see, is the increasing. So when the weight increased and the deflection increased. So why failure? Why the bridge will break? Because the limitation of the material and particularly joints weakness and lead to failure. Okay, so we can just skip this part, and you can see one by one. Okay, so let's conclude our presentation. So our conclusion is the deflection of popsicle stick increase when the weight of loads increases. So the stiffness of the popsicle sticks is 6.6 times 10 power of negative 3 and M power of negative 1. So thanks, doctor.